Hi, my name is Graham Wilson from the University of Glasgow, and these are my co-authors. Facial tracking in VR is seen as critically important to social presence. It drives embodied avatars and social interactions through animating avatar eyes, facial expressions, and even tongues. A number of commercial headsets include sensors for face and eye tracking, including the Meta Quest Pro used in this work and the Apple Vision Pro. So facial expressions are generally defined by the facial action coding system, which is used to describe all visually discernible facial movements and understand constituent parts. And it presents facial action units, FAUs, or just action units, AUs, which are activations of individual or component facial movements such as raising an eyebrow or dropping the jaw. And whole facial expressions have already been used as facial input in HCI. There are lots of examples, and we were particularly inspired by Taheri and colleagues. And so researchers used these large facial expressions, combinations of FAUs, as inputs such as happiness, sadness, or disgust. So facial input offers a valuable alternative input modality. There are 43 muscles in the face, a similar number of FAUs, even ignoring tongue and eye gaze, and each could be used as an independent input, depending on the level of control the user has over it. But facial expressions are overloaded. They intentionally or unintentionally convey emotion. They're modified by attention or cognitive loads, such as frowning when thinking, as well as communication when talking. And they're also quite heavyweight. Facial expressions involve the actuation of multiple FAUs and muscles. So our research process was first to identify individual candidate FAUs for input, so which AUs can be comfortably and accurately enacted in isolation, and how many different inputs are possible. We then trained an initial classifier to detect these FAUs based on the study data, and then run a second study where participants used the best candidate FAUs in two applications, a VR game and web browsing. So as mentioned, prior work is focused on holistic expressions, and we wanted to establish the utility of individual units. But it's also important to look at the detection of FAUs on commercial VR headsets, as it's more indicative of the real-world feasibility of the sensing using commercial sensors, and it would also allow for the immediate use of this input in applications as the functionality is already there. So our study used 20 participants and the Meta Quest Pro headset. We examined the 53 FAUs which are listed in the Meta Movement SDK, where participants performed 3 trials of each FAU, holding it for 3 seconds with a resting state before and after, logging the activation of the unit at 20 Hz. Participants rated the discomfort of performing the unit, the amount of effort it took to perform, as well as their overall level of performance in applying it. We then calculated the responsiveness of the unit, how quickly they reached the maximum activation, and an overall usability score based on the sum of the measures. Inside the VR headset, participants saw an animated avatar, which was enacting the FAU to be performed, and they had to mimic that as best as they could and hold it for 3 seconds, 3 times. For the full results, please see the paper. In general, we identified a usable set of FAUs, those which were comfortable, required low effort, and led to high performance, and which were also viable inputs. They were responsive and had a clear activation profile. And from those, we've identified 4 best candidate FAUs, considering Pareto optimal rankings and overall performance scores, and 3 out of the 4 of these are symmetrical or bidirectional, as in both sides of the face, offering a wider range of inputs. Other units may well be viable, and actually may be preferable depending on the user or the metric in question. So here we see the lid tightener, left and right, jaw drop, cheek puff left and right, and mouth left and right units chosen. So the Quest Pro outputs all detectable activations at once, so all units which are currently being activated to any degree, and so it's not always clear in raw terms from the data what action unit is being performed. And so we trained a neural network to recognize the activation of our usable FAUs using the same dataset from study 1. Data was split 80-20 into training and testing, with a resultant F1 score of 0.95 and a classification accuracy of 98%. And so we then applied our usable FAUs and the recognizer to general purpose XR interaction. We used 2 tasks, a VR game with common inputs and interactions, and an AR web browser for everyday interaction. The control scheme and mappings from FEUs to applications were mouth left and right for turning left and right in the game or scrolling up and down in the web browser, or alternatively using cheek puff left and right to turn left and right or scroll up and down depending on the user preference. Jaw drop was used to move forward in the game or select in the browser. Lid tightener left was used to interact in the game or move back in the browser, and lid tightener R was used to shoot in the game. Here we see a participant interacting in the game, first selecting buttons, and then performing selection and manipulation by placing blocks into set position. And then shooting some targets. After finishing these 3 tasks, a wall would open up to the side, and they would have to navigate through a maze. And here we see the web browser, where the participant is scrolling down, selects an article, scrolls down again, scrolls up, and moves back. Our design had 2 factors, so input and task. Input being facial inputs or traditional VR motion controllers as a de facto baseline, and the task was a VR game, which had to be used for at least 5 minutes, and the AR web browser for a minimum of 4 minutes and reading at least 3 articles. We used a within-subjects design with 13 participants, although 3 dropped out due to cyber sickness. All participants did the VR game first, as it included a training and familiarization section for the FAUs, and then the web browser, and the input order was counterbalanced within each task. What we found in terms of the physical impact of using the input methods was a significant difference in the Borg exertion for both input and task. So facial input saw slightly more exertion, but there was a small effect size. There were no significant differences in cyber sickness, but there were significant difference in TLX workload for both input and task, face leading to more workload than controller, and game leading to more workload than browsing. In terms of usability, input methods significantly affected all scales, with facial input unsurprisingly being worse than controller input, although they're still broadly considered usable, as most responses were above neutral on scales. And calibrating each per individual would likely improve usability. For social comfort, the controller was more socially comfortable to use in both public and semi-private spaces, likely due to concerns over the visibility of facial expressions. However, social comfort was comparable in private scenarios, and there was a high willingness to use facial input if no alternative controls were available. During interviews, 6 participants noted some positive aspect regarding usability of facial input, and the browser in particular exemplified the benefits of casual hands-free interactions, allowing users to interact without controllers or encumbrance. However, facial input suffered from reliability and fatigue concerns, particularly for prolonged inputs. Directionality was also confusing for some, as in which side of the face should be used to scroll down, and concurrent inputs, so performing multiple individual FEUs together, were often problematic due to conflicting or overlapping muscles. So in summary, it's been said that for a system to be genuinely accessible, every interaction is possible with at least 2 modalities. And facial input is a viable, multifaceted alternate input modality for XR. Headsets already have the sensing including, so it can be used to unlock more than just social presence. And we identified some of the most usable facial action units, although other units may be viable depending on preferences and calibration. Our demonstrators show viable control schemes for both spatial interaction and 3D navigation, offering potential accessibility benefits for situational, temporary, or permanent impairments. Users can successfully target specific FEUs rather than leveraging Gestalt holistic expressions, which increases the potential input space, many FEUs often symmetrical. And so facial input offers hands-free interaction out of the box.